So the other type of sequence and series we're going to be taking a look at is, as I promised you, geometric ones. And the key idea with the geometric one is that the method that they use to move forward is by multiplying repeatedly by some sort of number. So take a look at these examples here. You can see with this first one, going from 3 to 6, 6 to 12, 12 to 24, 24 to 48. This one is a consistent multiply by 2 each time. This next one, it's a little trickier, but the idea here is it is perfectly legal to multiply by a negative number each time. And if you repeatedly multiply by a negative number, it's going to force your answers to come out positive, then negative, then positive, then negative, and switch back and forth like that. And one other possibility that it's very important to be aware of is that you could multiply at each stage by a fraction. And here, each stage is multiplied by 1/4. I have to warn you, though, it's very tempting to think about this as dividing by 4 instead of multiplying by 1/4. And normally that would be perfectly acceptable. Normally thinking of it as division would be a reasonable thing to do, and I would probably even call it division. But because of the way the formulas are going to work out here, it's really important to actually know what number you're multiplying by and do not convert it into division. So for this situation in particular, don't think of it as division. Continue to force yourself to think of it as multiplication, even if it's multiplication by a fraction. Then, just like what we did with arithmetic sequences, we want to first come up with a formula for individual terms. So if you take a look at the string that you get, creating this in the described fashion, where you have some kind of starting number, and then you multiply by something, which, by the way, we call it R for ratio. Here the ratio from 3 to 6 is 2, 6 to 12 is 2. Here the ratio was -3. Here the ratio was 1/4. So we use the letter R to stand for ratio. And if you start with some particular A, and you multiply by R, then this is A2. This is A3. This is A4. And you'll notice each time you multiply by another R, that really just cranks up the exponent one more step each time. So the formula here should be pretty obvious with just one little twist. It's pretty clearly A1 R2 something, but here's the problem. It's not R to the n. It's not the same as whichever term you're on. Like when we were on A4, we didn't get R to the 4. When we were doing A3, we didn't get R to the 3. It's always one less. And that's actually really similar to what we had back when we were working with arithmetic sequences in series. We had an n-1 there as well. So there's a pretty decent chance that this will make sense to you right off the bat, that this will seem like a pretty reasonable formula for sequences. Now, unfortunately, the formula for series is not at all as easy as it was when we were doing the stuff in section 14.2. Here, the formula for the series has a much more complicated form to it. We're going to build up to it in a very similar way. We're going to take a look at what we mean when we say add up the first n terms. And remember, this down here, this is an, the nth term at the end, and so it has an n-1 for the exponent. But it's a good idea to think about what the previous terms were before you reached the end, where you had a couple of terms in there where the exponent was even smaller. Before you got to n-1, there was an n-2 before that, and before you got to that, there was an n-3 before that. So towards the end of the series, if you work your way backwards, the exponents get smaller, just like at the beginning. If you go forwards, your exponents get bigger. And then here's the thing that we do in this case. We don't simply rewrite the series in reverse order like we did last time. That wouldn't actually do us any good here. You wouldn't get a consistent total because the amount that it increases on the left is not the same as the amount that it decreases on the right. It's going up and down by a ratio, not by adding or subtracting. Instead, what we do is we go through the whole series and we multiply by r. And this is going to seem like a bizarre choice at first, but hold on a sec. You'll see how it comes together. So this first term is now going to be a1 times r. And the second one, since we're multiplying by an r, it's now going to be a1r squared. And this one, since we're multiplying by an r, the exponent will go up to 3. And if you think about it, throughout the whole thing, multiplying by r is just basically going to take every exponent and increase it by 1. So this one down here would be whatever n was minus 2. This one would be minus 1. And here, if we're increasing the exponent by 1, it's going to go up to r to the n. And then what we do here is we subtract. So it's not like adding like we did last time. Here we're going to subtract. So we're going to have Sn minus Rsn on the left. And then here's the important part. If you're subtracting the blue stuff from the stuff right above it, notice that these two terms match up. So when you subtract, they're going to cancel out. So you're going to start with a1, but then you're not going to have an a1r because subtract a1r, it's going to cancel. And you won't have an a1r to the second because this one down here in blue is going to cancel with it. And the next term was going to be an a1r to the third next. Well, that's going to cancel with this one, and so on. They're all going to cancel sort of zigzag from each other all the way down through this whole list until towards the end, there's one last number that doesn't cancel with anything. There's this a1r to the n at the end of the second list that doesn't have anything above it to cancel with. So, this is not quite a formula, but it's really close. All we have to do is factor out Sn and factor out an a1 from this, and we end up getting the following formula. The formula for a geometric series is a1 times 1 minus r to the n over 1 minus r. So that is a much more complicated formula than what we had in section 14.2. The applications that you use these sorts of formulas for are also fairly complicated. For example, let's say that you have sort of like a retirement account where you're putting $100 into the bank at the beginning of every year, which isn't a lot of money, but hey, maybe it's like a little support account that you're going to have just so you can buy yourself something nice in 20 years. We want to figure out how much is going to be in the account at the end of that 20 years. And the trick to this type of problem, the really sort of special trick to this, is to treat each deposit as if it's its own separate account. So we've got deposit number 1, which was put in back at the very beginning. So that's going to be $100. And then every year it's gaining 5% interest. So really, I guess I could just say 1.05. And it's going to be in there for 20 years. So it's going to be 1.05, 1.05, 1.05 over and over and over again for 20 years. And then treat deposit 2 as if it was going into a different account. Like you're treating it completely separately from the other one. Deposit 2 happens a year later, so it only gets 19 years of interest. And when you get to deposit number 3, same idea, and you can sort of see where this is headed. Deposit number 3, it's in there for one less year, so it only gets 18 years of interest. And so on, and so on, and so on, until you get to the very last deposit, deposit number 20, which happened at the start of the very, very last year, so it's only in there for 1 year. And then, if you really want to figure out what the total is, you have to add them all up. If you add them all up, we are doing a geometric, because notice how the exponents are, if you go from the bottom to the top, the exponents are growing and growing and growing. And it's a series, because you're adding them all up, so the formula says we're going to be doing a1 times 1 minus r to the n over 1 minus r. Copy that down. And we're going to think about this from the bottom up, because I think it's easier to see how what r is and what the exponents are. So a1 is 105. That was the starting amount down at the bottom of our list. The ratio is this thing that we keep raising its exponent. So the ratio is 1.05. N is 20, because we're doing this over 20 years. And you'll notice that maybe when you were working with arithmetic series in section 14.2, you could have maybe done those problems by hand with pencil and paper, but this is clearly not a problem that anybody would expect you to do with pencil and paper. You grab a calculator, you type it on in, you let the calculator do the work, and you get $3,471.90, well, it's 925, so it's 93 cents. Now, this is not the end of our discussion about geometric series, because there's one other issue that's a little bit tricky. It has to do with the idea that with geometric series, it's actually possible to talk about adding up an infinite series. The idea here is if you were to try to apply the formula we had just a second ago, and let's say that you tried to plug in infinity for the exponent up there, which, yeah, that's not entirely legal because infinity isn't actually a number. You can't plug it in like you could plug in 20 or 37 or something. But let's pretend and let's try it and see what we get. Well, here, a1 would be 16. R, well, let's see, what's the ratio? To get from 16 to 2, to get from 2 to a quarter, to get from a quarter to 1 over 32, the ratio here, and if you're ever not sure, you can just actually literally work out a ratio. Take one number and divide by the previous number. The ratio here is 1/8. So when you plug everything into the formula here, you've got this. And notice that as long as that r is a pretty small number, like a fraction, then this kind of thing here is basically saying 1/8 times 1/8 times 1/8 forever. And each 1/8 you put on it makes it even smaller and smaller and even more smaller. So eventually this thing is going to be, and I'm going to put this in quotes because this isn't a mathematical term, but it's going to be infinitely small. So then the question is, if something is infinitely small, what is it? Well, there's an easy answer, and the easy answer is the obvious one. It's 0. So this whole formula actually becomes simpler. You would have 16 times 1 minus 0 over 1 minus an 8. Well, wait a sec. 1 minus 0? 1 minus 0, that's just 1. So this is really just 16 over 1 minus an 8. So that's 16 over 7/8. So that's 16 times 8 over 7. And let's see, what's 16 times 8? 80 and 48, so 128 over 7. There we go. So the formula for an infinite geometric series is an actually pretty simple formula. It says that, like we just had here, since that 1 minus 0 thing, that if you're trying to add up an infinite geometric series, it's just a1 over 1 minus r. The whole 1 minus r to the n part turns into 1 minus 0, so that part just basically drops out and you don't need it. It's so much easier than the regular formula that in many practical circumstances, where maybe technically you're supposed to do a finite series, it may be actually easier to do an infinite series. Like, for example here, The first part of this question says, how far does the ball travel in 10 bounces? Well, we're talking about a ball that goes 3 feet up and 3 feet down. So 3 up, 3 down means a total of 6 feet. And then on its next bounce, it only goes a third of the previous bounce. So it's 1 up and 1 down for a total of 2 feet. And the next one after that would be 1/3 up, 1/3 down for a total of 2/3. And oh look, what do you know? That's a geometric series. So if you were going to do 10 bounces of this thing, for 10 bounces, your formula would be S sub 10. It would be A1, which is 6, 1 minus R, well, R here is a third, to the 10th, over 1 minus a third. Now, I don't know what 1/3 to the 10th is, but I'm 100% sure that it's a calculator question. And if I were to feed that into the calculator and type through all of that, I would end up getting, it turns out, 8.999847, some sort of messy decimal. Real mess. Super ugly. But if you kind of pretend, like it says in the second part of the question, that the ball is going to bounce forever an infinite number of times, the formula is actually easier to deal with. It's just 6 over 1 minus a third. And you don't need a calculator for this one. This is one that you could work entirely by hand and get 9. Which, 8.999847 versus 9? 9 is the same answer to 1 decimal place of accuracy, to 2 decimal places of accuracy, to 3 decimal places of accuracy. These are the same answer. So there are a lot of places in even like engineering where you would think they would be really careful about details, where sometimes it's perfectly fine and frankly easier to just do an infinite series rather than try to work out the finite series. The point here is, for geometric series at least, infinity is a way to simplify the problem.